All right. Do you guys feel like things are accelerating? Anybody? Yeah. Okay. Me too. All right. I'm going to talk about why that is. And to tell this story, we're going to go back in time, like way, way back in time to 2023, when I built a programming agent called Tiny Agent. It was command line based and about 400 lines of code, and it really worked even back then. And I was like, wow, this is incredible. A small wrapper around GPT-4 makes this totally general purpose tool that I can talk to and get to do programming work for me. And it felt like a secret glimpse into the future. And then in 2024, a lab from Princeton released this amazing benchmark called SWE-Bench that tries to measure how good AI is at doing real-world software engineering tasks. SWE-Bench quickly became the world's yardstick for how good AI is at programming. And then in September 2024, OpenAI released O1 Preview, the world's first reasoning model. I was super excited about this because the top issue I saw with my programming agents was that they make what I call reasoning mistakes, logical errors in the way they process data. So I decided to attempt to be the first to top the SWE-Bench leaderboard by using a reasoning model. And on January 17th, 2025, I'm happy to report that I did it. Thank you. My submission used OpenAI's O1 model and held the top position on the public leaderboard for 2 months. So how did I do it? The answer? Deadlines. My son was born the next day, so I knew I needed to get that result. I grinded it out. Kids are really great. Okay, but the real key to success for building AI applications is experimentation. And I ran lots and lots of experiments, all tracked with Weave, which is our tools for building AI applications. I'm mostly going to talk about that experimental process. But let me back up for a moment and show you what an agent fundamentally is. Agent is composed of two things. There's a model, which is typically an LLM, and a harness. The harness is code that an application developer writes to give the LLM real-world capabilities. The harness has a few responsibilities. It implements the agentic loop so the agent can take many steps in a row. It provides a set of tools the LLM can call to take real-world actions. Tiny Agent provides the read file, write file, and run command tools. That's all it takes to build a programming agent. The harness records the sequence of prior steps as memory, and it formats the memory available tools and instructions into prompts to send to the LLM. Now, to make a good agent, you need a way of measuring performance. We do this by defining an eval. Eval consists of a set of problems and a scoring function for determining correctness. The problems in SWE-Bench are real Git issues across 12 open source repos. The scoring functions in SWE-Bench are unit tests that determine if an issue is correctly solved. The job of an agent developer, then, consists of two things: define and improve evals to better measure real-world performance, and run experiments to improve the agent against the evals. As my colleague Tim says, define the hill to climb and then climb it. Okay, so what kinds of experiments can you do? With any experiment, it's best to change one thing at a time. Otherwise, you don't know which change caused an effect. So one style of experiment is to keep the model fixed and improve the harness. This is all the experiments that I did. I used OpenAI O1 as the model and ran lots of experiments to improve my harness. So for example, I did experiments changing prompts to give the agent different instructions. I added a memory compression system so the agent could run for longer. And I added new tools like a Python-specific code editor. But you can also keep the harness constant and vary the model. Here, one thing you could do is swap the model. So for example, today, I could just swap to O3 and see if I get better results. And this is really easy to try and can be done just by changing your experiment configuration. But what about actually training the model to make the agent better at its task? We'll come back to that question a little later. For now, let's take a deeper look at the experimental workflow in which we do our experiments. So the experiment loop starts with the research phase, where we look through our database of prior experiments and decide what to do next. Here we find an example where our programming agent can't figure out how to run the unit test in the repo it's working on. So we use this research to think up an idea. Let's update the agent's prompts to say there is definitely a canonical way to run the unit test. In the implement phase, we implement our idea as an experiment spec, which is a combination of code and configuration that will run our experiment. Here we add a line to our agent's prompt in our code editor. Finally, we run our experiment, producing a new result in our experiment database, which is W&B Weave, that we can use for further research. So those three activities, research, implement, and run, make up the experiment loop. Just do that 977 times, and you'll get great results. But that's not exactly the case. There's one really important activity that you can do, and it's one that I do a lot. The last activity is to take a look at our workflow and see how we can improve it. We can build useful tools that improve the quality of our ideas, and we can build frameworks and infrastructure to make our loop faster. This is our job at Weights and Biases. We believe that tools are an incredibly high leverage thing to work on because they help the world make more progress. So now I'll show you how I improved each phase of the experiment loop for myself and how we're bringing those improvements to our users. First, we'll look at speeding up the implementation phase, where we take our new idea and implement it in code as an experiment. One way to speed up implementation is by making new frameworks, libraries, and languages to help users better express their ideas. I created a new framework called PhaseShift that I use to do this work. It's written in TypeScript, it has composable environments, models, agentic controllers, and more. And it's not released yet, but we'll get it to you soon. Actually, is Zubin here? Yeah. Zubin started on Monday to work on this stuff with me. And I haven't had a chance to catch up with him yet because I've been working on this talk. But Zubin, I think this could be a good starter project. Another way to speed up the implement phase is something I hope every programmer here is now doing, which is use AI editors like Windsurf to assist in the development process. These tools made it way easier for me to build the PhaseShift framework and implement all of my experiments. And these capabilities are rapidly improving thanks to reinforcement learning, which we'll talk about later. Full-blown programming agents like Claude Code are able to perform longer tasks unassisted. So the implement phase is getting faster and faster because AI models are improving so fast. Next, let's talk about speeding up the run phase. This is the phase where we take our experiment spec and run it on infrastructure. So SWE-Bench is a complex eval. You need to orchestrate agents working in Docker containers, and a single problem can take an hour or more end-to-end if the agent can do complex things like running expensive tests. So you want to make this really fast so you can run more experiments. You want high parallelism and good resource utilization, and this requires a lot of infrastructure and performance engineering. So early on, I created a container management server that runs on a large cloud VM. All the Docker images for SWE-Bench are always cached there, so environments start up instantly. The primary agent code runs on my laptop, calling out to the LLM provider in the container server to run the agent loop. So with this, I could happily run hundreds of parallel examples, and this is how I did it for all of my experiments. But there are some problems with this. This is the first problem. Running long-running processes on your laptop is not a great experience, because if you leave your Wi-Fi network or somebody closes your lid, the job dies. The second is it's hard to manage lots of parallel experiments when they all run in different terminals. You quickly lose track of which experiment is where. It's just this unwieldy mess. So you're pretty limited on how many experiments you can do, because a single laptop is a bottleneck. Thankfully, we have a solution for this. It's called W&B Launch. Users can queue up units of work we call jobs from the command line or the W&B UI. Then the W&B backend starts the jobs in a compute cluster as capacity becomes available. But how do you get a compute cluster connected to the W&B backend? Now, here I need to give a little backstory on Launch. We shipped the initial version in 2023. It was designed to be super flexible and supported connections to multiple backend targets, SageMaker, Vertex, Kubernetes, and more. Unfortunately, that flexibility made it challenging for us to deliver an excellent experience with a small team. So at the beginning of this year, we made the tough decision to put Launch into maintenance mode so the team could focus on scaling other parts of the W&B product. Very, very sad. But being part of CoreWeave changes the story for us. We now have direct access to the world's best AI infrastructure and the team that builds it. So I'm excited to announce that we're working on bringing Launch back, starting with a public CoreWeave cluster for W&B AI users. This means there's no longer configuration or backend setup needed to start Launch jobs. And by tightly integrating Launch with the backend technology, we can build a much better experience for end users. It'll be seamless. Launch was built as a tool for general AI workloads, but generality is hard to get right. So again, with the goal of providing an excellent user experience, we're focusing on making Launch great for running evals. To that end, we've created two powerful pre-built Launch jobs for evaluating AI models with off-the-shelf benchmarks. Here's how it works. For evaluating against a hosted model API, pick the eval API job. You fill in the required fields, pick the W&B CoreWeave queue, and click Launch, which is off the screen there. Our brand new runs drawer shows you in-progress runs, and as Launch gets started, your job started in the cluster, it'll transition from queued to running. From there, you can click through to the W&B workspace for analysis. Or you can view the evals in Weave's evals view. And we automatically create a Weave leaderboard so you can compare models across all the evals you've tried. From the leaderboard, you can drill into specific evals to see example-level details. Or you can select models for comparison, select your eval, and see high-level charts for analysis, and drill down to dataset results for fine-grained information. The second new evals job can evaluate a save model checkpoint. It automatically spins up a VLLM server on a GPU in the CoreWeave cluster to host your model's inference, and it runs the evaluations against that server. This is especially useful for fine-tuning jobs where it's important to make sure your new fine-tuned models are at or above baseline benchmarks. So what about customization, like running your own evals or harnesses? This is where Launch really shines. Just fork our public evals on your laptop and plug in your own harnesses or evals. Then you can launch experiments to the cluster with a simple command or configure and launch new experiments from the UI. So we're bringing evals on Launch to private preview soon. Reach out if you want to give it a try or have any ideas. Next up, we'll work on increasing the complexity of supported jobs. We'll add support for orchestrating external containers for evals like SWE-Bench, and we'll add other job types like fine-tuning. We're initially focused on making a great experience on the public CoreWeave cluster, but we know data privacy is critical to our enterprise customers, so later this year we'll bring back supported private Kubernetes clusters. So that was optimizing the run phase. Now let's look at optimizing the research phase, where we analyze past experiments to decide what to do next. How can we improve the quality of ideas that we generate? As I said earlier, I use W&B Weave as my experiment database, and I spent tons of time in the Weave UI pouring through traces and results. But there are always new types of analyses to do on data-heavy problems. Weave makes it super easy to export your data either as CSV files or from APIs. So I built lots of custom tools. At first, I relied heavily on spreadsheets and a bunch of custom Streamlit apps. But those tools are limited in what they can do. So over time, I vibe coded a completely custom React UI called the PhaseShift UI. It has a charting capability that's useful for monitoring evals as they run to see if they're headed in the right directions, and for doing analyses like looking at token count versus resolution curves. And it has a powerful table that you can rapidly configure to compare evals at the example level. This is really useful for error analysis and regression analysis. And finally, it has a custom view for agent trajectories, lets you quickly see the tool calls and edits an agent made at each step, with deep links into the Weave UI for details. Now, that UI may be shipped with the PhaseShift framework later. In the meantime, we're doing a couple things. First, we're integrating a lot of these features into Weave UI itself. This is a screenshot of the upcoming Weave Plots UI, where you can construct rich dashboards from any trace and evaluation data you've saved. We've also recently shipped some great new eval analysis features. This is a demo of our new datasets results comparison UI, which is live now. Pick some evals and click Compare. You get our powerful comparison charts and this new Datasets Results tab. Here we configure the table to show columns we need for our regression analysis. Then we multi-sort by the resolve column. Now we can easily see examples that our latest eval regressed on. From there, we can drill in to find differences in outputs at the example level. And drilling down to the trace view, we can use the new trace sliders to easily flip through complex agent sequences to find what the agent did wrong. But AI is getting really good at building web apps. So we're also making it as easy as possible for you to vibe code your own tools. To do that, we've released the experimental W&B AI UI repo, which is a library designed for LLMs to build Weave data applications. It comes with an example prompt that actually generates that entire PhaseShift UI that I made. So instead of giving you the PhaseShift UI directly, we're giving you a prompt that generates it. How cool is that? You can generate it for $20 with Opus 4 and Claude Code, and you can customize it any way you want. Is this the future of tool development? Go try it out. OK, so we've looked at techniques for improving each phase of the experimental workflow. Each improvement we make to the phases of the loop accelerates our future progress. The next question is, can we use AI to automatically improve the experimental loop? So we're starting to see some signs that the answer is yes for some tasks like SWE-Bench. One example is this really cool paper from a few days ago called Darwin-Gödel Machine: Open-Ended Evolution of Self-Improving Agents. Here's how it works. First, as the DGM algorithm runs, it maintains a tree of agents and the SWE-Bench eval scores that each agent achieved. This is the set of agents our algorithm has produced so far. Next, we select an agent to serve as the parent for our next experiment. The paper uses some statistics to do this selection. It favors agents with higher eval scores and fewer children. But crucially, there's a non-zero chance that any agent can be chosen. This ensures what the paper calls open-endedness. Then we do one pass of the experiment loop. In the research phase, we only consider a single experiment, the parent that we just selected. We feed traces of the problems the parent was unable to solve, along with the parent's code, into a single OpenAI O1 LLM call. And then we ask the LLM to come up with a single idea for an improvement. So this is a way of using AI to do error analysis to come up with something to try next. The selected parent agent is then used as the coding agent to implement the idea. So notice how cool this is. We're generating new agents that write code for future agents. So this is a self-improving algorithm. Finally, the DGM framework runs the experiment, adding a new child to the tree with its new eval score. The paper shows some pretty cool results. Combining open-endedness, which makes it possible for the algorithm to use worse-performing agents as stepping stones to better ones, and self-improvement, where the algorithm uses newly generated agents to write code for future ones, is the recipe for the best results. This chart shows the actual improvements that led to the best final agent. What's really interesting to me is these are very similar to the set of improvements I made and even the order in which I made them. I first added more granular file viewing and editing. Then I added a memory to make more of the agent history fit into the LLM context. And then I added multiple patch generation and ranking, which is the same thing that this algorithm did on its own. So this is incredible to me. I spent 2 months doing something that I thought was pretty smart, but it seems AI may be able to do this completely automatically and way faster. OK, so am I out of a job? Not yet. There are some serious limitations with the agent building work I did and what algorithms like DGM can do. Like the DGM algorithm, I only improve the harness in my SWE-Bench experiments. So doing that will always be limited by the model's capabilities. Ideally, we want to be able to run the agent on example problems, score its solutions, and then use the resulting data to update the model's weights to do better next time. This sounds great in theory, but we didn't have the recipe for doing it. Until January of this year, when DeepSeek surprised the world with their R1 reasoning model and its supporting paper. That DeepSeek paper gives us a recipe for getting reinforcement learning to actually work on LLMs. The recipe is an algorithm called GRPO. Prior techniques like supervised fine-tuning allowed us to train LLMs on the exact outputs we wanted. Reinforcement learning allows us to instead specify what the final goal is without specifying the exact steps the model has to take to get there. This technique is used to teach LLMs like O1 and R1 to reason by asking them to produce a sequence of thoughts before their final answer. As shown on the left, the LLM learns to output longer and longer sequences of thoughts prior to answering. And as shown on the right, the LLM's answers become more accurate as it learns to think for longer. RL can also be used to directly train models for agentic tasks. We specify the agent's goal, and the model gets better and better at taking the right steps towards solving the problem. All you need is an eval like SWE-Bench, and you can directly train your model to get better results using this technique. So now we have the recipe for directly training models to get better at agentic tasks. But what about the tools? We're in the unique position that we build tools both for training models and applying them. And reinforcement learning gives the world the ability to directly train models for applications. So I'm super excited to announce that we're integrating these tools much more tightly to bring you the best tools for reinforcement learning. With that, I'm super excited to bring Kyle Corbit to the stage. As the founder of OpenPipe, he's been building tools for fine-tuning models for a long time. His new art framework makes it super easy to do RL on agentic tasks, and it'll be the first framework to support models and weave together.
Hey, everybody. Very excited to be here. Thanks, Shawn, for inviting me. I want to talk just a little bit about what art is and what we're doing. So ART, it stands for Agent Reinforcement Trainer. It's basically a way to use reinforcement learning to directly optimize your agents and make them more reliable. The way it works is you bring your agent, and wherever you've defined it, whatever framework, or if you've built your own framework, you can bring it directly into ART. And then you have to define a reward function, which is another way of saying an eval, a way of deciding when the agent has finished to run, if it did a good or bad job. Once you have those two things, your existing agent and that eval, you can use Art to directly optimize your agent on that evaluation and improve its performance over time. And we find that this helps a ton on both capabilities and also especially reliability, making sure that the agent actually is able to successfully deploy. Very briefly, I want to talk about one customer we've been working with for the last couple of months and their experience. So this is a really large financial services firm. It's actually one of the top 3 asset managers in the world. They have over 50 million customers. And they've had an internal team that's been working on deploying a customer support agent for the last 18 months. They've never actually gotten it into production because they found that even with all of the guardrails they wrote and all of the different frameworks they tried, they were never able to get the hallucination rate on their agent below about 2%. And as a very large firm with high internal standards and in a regulated industry, that was too high and they felt like they couldn't deploy it. So we've been working with them for a couple of months. And we found that using the ART framework and the agent they had worked on before, we were able to get that hallucination rate down significantly below 1% and to a level that they were comfortable deploying. And this is possible because they were able to define an evaluation of what a hallucinated answer looked like, and so we were able to directly optimize against minimizing the chance of that happening. And of course, this is something we can do with anything. The part I'd like to announce now, and that we've been working with Shawn and the team at Weights and Biases on, is how we can directly integrate Weave along with Weights and Biases model product to very quickly iterate on these and track experiments and go faster. So this is an example of the existing models interface. There's a lot of these metrics that we find are really helpful. A lot of these are ART framework track automatically. Some we add per job. The new thing that's going on here is we have a new Weave tab up here. So this is showing the actual rollouts or agent traces for every single one of our runs. And this is super helpful for debugging. So like we can look here at scenario 14 and track it over time and see when it's getting the answer correct and when it's getting it wrong. And so this is really helpful because it quickly lets you identify what's going wrong. So we're going to click on one of these examples where we got the answer wrong, and we can see through our metrics that the problem was the tool calls. Let's look at that. And again, in this interface, we can actually, in a very granular way, see what the agent's doing and what it's doing wrong. In this case, we've got a bad tool call format, which is why the run is failing. And we can take that back into our reward function and start penalizing that so that the performance improves over time. So together, this makes the feedback loop and the cycle much, much faster, so we can identify those issues. And of course, once we've identified those issues, we use the reinforcement learning to fix them really quickly. And that's, what I want to talk about.
Yeah, so if you have a chatbot that's hallucinating and you want to fix it, talk to Kyle. All right, we're very excited about reinforcement learning. It gives us a powerful mechanism for improving agents, and we think the combination of these great tools will make RL accessible to everyone. Now, back to the limitations we were discussing earlier. The second limitation is the eval we're optimizing against is also static. The algorithm can never do any better than maxing out SWE-Bench. And while maxing out SWE-Bench would be awesome, in the real world, we constantly create new, harder evals as we make progress. The third limitation is that the DGM algorithm automates all the phases of the experiment loop, but it only improves the implement phase, so it can't improve its own ability to generate ideas or run experiments more quickly. Okay, so how do we solve these remaining problems? So far, this talk has been all about programming agents. But to make a truly self-improving algorithm, we need to build a researcher agent. Researcher agent is an agent that can do all the jobs of a researcher, which is the same jobs as the agent developer we talked about earlier. First, it needs the ability to build evals. The tools an agent has define its capabilities, so we give the researcher a create eval tool. Next, it needs to be able to run experiments, which means it needs to be able to do all the phases of the experiment loop. For the research phase, we give it the ability to query the experimental database and another ability to write a report with an idea. Since this is an agent, it can choose how best to perform the research, where to focus, and how to break the problem down into substeps, unlike a more rigid algorithm like DGM. For the run phase, we give it the ability to launch jobs, so it can run and manage lots of parallel experiments on large compute clusters. And for the implement phase, we give it all the abilities of a programmer agent. The first few tools here can be implemented using the Weights and Biases APIs. The others are standard tools programmer agents use. In other words, a researcher agent is a programmer agent plus the ability to use weights and biases. Okay, what can the researcher agent do? Just like an AI researcher, a researcher agent can improve any target AI system by defining ways to evaluate it and performing the experimental workflow. If you have a protein folding model, you can ask the researcher agent to improve it. If you have a climate forecasting model, you can ask the research agent to improve that. Or the researcher agent can improve a programmer agent. Ultimately, you can ask the researcher agent to improve itself. By the way, if you know any researcher agents, let them know about my new book, Self-Improvement for Researcher Agents. Somebody asked me if this is a joke. This is a joke. I'm not releasing a book. I'm not allowed to moonlight in my new contract. So we've gotten this started by creating the W&B MCP server, which you can connect to an agentic LLM like Cloud Code. Currently, the MCP server gives the agents the ability to do research on W&B data. Soon, we'll add support for creating evals and launching jobs so you can build complete researcher agents. OK, time to wrap this up. So how close are we to self-improving AI and the intelligence explosion? We're certainly not there yet. To me, this feels like 2023 when I first started thinking about programmer agents. As I found with Tiny Agent, you could actually build a programmer agent that did useful stuff, even way back then. But even now, programming is not a solved problem. We're using programmer agents for longer tasks, but they have plenty of flaws. For researcher agents, it feels like that beginning. It's the right time to start playing with these systems. They'll probably be useful in narrow ways even now. OpenAI's SWE-Bench is a good initial yardstick for where we are, and it's a 20% solve rate today. Over the next year or two, AI will assist researchers more and more in their work and start to automate more parts of the job for some problems. I'm very excited about the role weights and biases can play in this. We'll make our APIs more AI-friendly, build AI assistance features for researchers, continue scaling up the amount of data we can handle, and start work on researcher agents that you'll be able to use to help in your work. Because researcher agents use our APIs, we'll have the same visualizations and capabilities that you all are used to. You'll be able to see what researcher agents are doing and work alongside them. Over time, we'll evolve our UI to support this human-AI collaboration in deeper ways. And while I don't know exactly how all this will unfold, there's one thing that I do know. It's going to require a lot of compute. So get out there and buy some GPUs. Thank you.